In this goal, we will be talking about pH and other related equations. Let's start off with pure water ionization. Water self-ionizes. Now, not very much. Most of it is H2O, but a slight amount will split apart and I will get hydrogen ion and hydroxide ion. The hydroxide ion, this is your base molecule, and your hydrogen ion, as we've mentioned before, this is your acid molecule. So you see that water can split apart and form an acid and a base. It strongly favors the reactant side, so this doesn't happen very much. So in my beaker of water, I might have one water molecule that has fallen apart like this. So we can write an equilibrium expression for water because it is at equilibrium. And we know that because of our double arrows here. So we call our equilibrium constant, instead of the KEQ, which is general for anything, we call this one specific for water the KW. And so I do products over reactants, but if you look on the reactant side, I only have liquids. So it is only my hydrogen ion times my hydroxide ion, and that equals KW. Now KW is defined as 1 times 10 to the negative 14. So just by definition. Now if you look at the equation listed above, and we see that we are at equilibrium, and I'm just going to clean this up a little bit. If I had a container of water, and let's say I put in a whole bunch of lemon juice, and lemon juice is an acid. So knowing Le Chatelier's principle, if I were to add hydrogen ion, what is going to happen to my equilibrium? Well, we remember add away is Le Chatelier's principle. So something that's at equilibrium, if you add it to one side, it will shift away to the other side. So I'm going to shift and form more reactants. Well, what does that do to my OH? Well, my OH, it decreases. So it's going to become less. Well, looking at this KW expression, if you have an increase in the H plus and a decrease in the OH, that's okay. That can still happen, that I can multiply their values together, and I will get 1 times 10 to negative 14. All right, let's just go back to just normal water. If you look at normal water and you look at our 1 times 10 to the negative 14 is our KW. If I were to take the square root of this, I could solve for both my hydrogen ion and my hydroxide ion. And here they are. They would both be 1 times 10 to the negative 7. So this is for water. So for water, the hydrogen ion concentration is 1 times 10 to the negative 7, and the hydroxide is also 1 times 10 to the negative 7. We see that they're the same. We see that they will be equal to each other. And that's because they're formed at the same time. One water molecule loses a proton, and I'm going to get the equal amounts of hydrogen and hydroxide ions. So in my container of water, right here, I see that I have equal amounts hydrogen ion and hydroxide ion at this point. And I can write that ionization of the hydrogen ion like this, 0.000001. Or another way that you can write this is 1 times 10 to the minus 7. So this number is really, really small, and there's a lot of oxygens. And so we often take and find the pH. And the formula for that is pH is equal to a negative log of your hydrogen ion. And the log button is just found on any scientific calculator. So how the calculator works, and you can try this right now, you will put in negative and then press the log button and then put the concentration. So either 0.000001 or 1 times 10 to the minus 7. And then when you press enter, you should get a 7. Some calculators work backwards, so I'd actually work this way in the formula. I'd put in my concentration, then press log, then press negative. So working backwards. Either way, you should get a 7. So you can do this problem in your head. So how I do the pH is I really just look for that exponent. And I ignore the negative, and I can just write it. let's say into my water, just like I said before, I dump a whole bunch of acid in it. Well, I'm going to increase my acid and decrease my hydroxide, so maybe I come over here. So now my concentration of my hydrogen ion is 0.1. I could also write it as 1 times 10 to the minus 1. So taking the pH of that, so the negative log, I would just write this exponent, that 1. So my pH is a 1. Okay. Let's say to my water, instead of adding an acid, let's say I add a base. Maybe I put in a whole bunch of hydroxide. So now I've shifted the equilibrium over here. So I still have a tiny bit of that hydrogen ion, and it's listed like this. Notice that the pH is always based on the hydrogen ion. So I have 0.1201, so I could write that as 1 times 10 to the minus 13. So when I take the log of that, I'm really just going to include that exponent. So again, try it out on your calculator and make sure you know how to use your calculator, but you also can just do it in your head if it's a simple numbered like this with just ones. All right, so what do we see? We see that if we add an acid, our hydrogen ion goes up, our hydroxide goes down. If we add a base to our water equilibrium, we see that our hydroxide ion goes up and our hydrogen ion goes down. pH is only based on the hydrogen ion, so the power of the hydrogen ion, and we see that the lower the pH, the more hydrogen ion. So it's a little bit backwards that way because that log makes this an exponential value. All right, so this pH is very handy. Because we get rid of all those zeros, we just have a whole number to work with. It makes it a little bit easier to manage. Here, there are some common household substances up here in this picture. 7 is considered neutral. So again, that's the pH of water, where it has equal number of hydrogen to hydroxide ions. If you go above 7, it is basic or alkaline. Alkaline is another name for saying I have a base. So a very, very large number means I have not very much hydrogen ion, instead I have more hydroxide ion. So we see things such as seawater is a little bit basic, detergent, a lot of your soaps and things like that will be basic. Household ammonia that you might use to clean your house. And then oven cleaner. Oven cleaner is a really strong base there. Less than 7, this is acidic. And we see that milk is just a little tiny bit acidic. We have coffee's acidic. Tomatoes, they are acidic. Soft drinks have phosphoric acid in them, so they are acidic. Stomach acid is hydrochloric acid, which is a strong acid. It's amazing that our stomach can make that strong acid. Let's look at that pH scale. So again, the pH scale is, we're only looking at the hydrogen ion concentration, and the pH scale goes from 0 to 14, but you can go above 14, and you also can go below 0, have a negative pH. That would be an extremely acidic solution. And here's that formula that I introduced to you last slide. The pH is the power of the hydrogen, negative log of the hydrogen ion concentration. And again, you can just look at the exponent to help you figure out what the pH is, as long as everything's a 1. Okay, so if you're exactly at a 7, then you are at a neutral pH. What does that log button do? So this is just a very brief math review. Your log button counts how many 10s there are in your number. So if you have a 10, that would be 1 times 10, or 1 times 10 to the 1. If you had 100, that would be 2 10s multiplied together. So 1 times 10 to the second. And 1,000, that would have 3 10s. So you get 1 times 10 to the third. So if you press your button on each of those, your log button, it counts how many 10s there are. Let's look at if you had 2,000, you would be a little bit above 3. I think it's like 3.3. So again, you'd still have 3 10s, but you'd also have a fraction more. So on ugly numbers like that, you would need a calculator to help you figure it out. Now in chemistry, we have very small numbers. So our small numbers, they count how many 1/10ths that we have. And you're going to get a negative number for these small numbers. That's why your formula for pH, you multiply it by a negative. So if you had log of 0.1, or this would be 1 times 10 to the minus 1, you would get a log of 1, so whatever that exponent is. And again, on your pH formula, we multiply it by a negative just to get rid of it. A log of 0.001 would have 3 1/10ths, so that gives you a number minus 3. If you have a log of 0.002, then you're going to get a negative 2.7. So it's a little bit different counting with smaller numbers. So let's use this formula, the pH formula, to find the pH for all these concentrations. And so some of these we'll be able to do in our head, and some of them we will need a calculator. So on this first one, we see that there's just a 1 times 10 to the minus 8. So I know my pH is 8. I just use that exponent. Get rid of the negative, and it's 8. On the second one, again, I'm going to look at the exponent. This is a pH of 6. And for my last one, this is kind of an ugly number, so I'm going to need my calculator. So you'll just press negative, log, and then you'll press the number, or you'll do the number, log, and then negative. It just depends on how your calculator is set up to handle these functions. So on this one, I have 10.17. And on the last one, I have 4.28. Here are some equations that are related to the pH. I also can look at that hydroxide concentration, and I can use it to determine the pOH. And it's done the same way. I take the negative log of the number. How pOH and pH are related to each other is through this equation. I also can go back to that water dissociation constant, and I can rearrange it to solve for the hydrogen ion concentration. And then I could take the pH. So the hydrogen ion concentration is equal to 1 times 10 to the negative 14 divided by the hydroxide, and that would help me find that hydrogen ion. You also could reverse this to solve for the OH concentration. And how do you go backwards? What if I have my pH already, but I want to do my hydrogen ion concentration? Well, you're going to raise it to the 10 to the negative pH. So a good example of this, if my pH was 7, I would take my 10, and on your calculator, you could use the 10 to the X button. You're going to take your 10 and you're going to raise it to the negative pH, and then you'll press enter. So this would be 1 times 10 to the minus 7. And I can just do that in my head. If you have a number that's kind of ugly, then, for example, pH of 7.2, you're going to do the same thing. Use that 10 to the X button, or you could use your 10 and then your caret button, and then negative 7.2. Do not leave it like that. That's not your answer. You need to press enter on your calculator. So these ones that aren't a whole number, they're a little bit ugly, but you can still do them. Just make sure that you press enter. So the hydrogen ion concentration here would be 6.31 times 10 to the negative 8. So that's how you would go backwards. So let's use these equations and go through and solve for the following problems. So the first one says find the pOH if the OH is 1 times 10 to the minus 12. So if I were to take the negative log of this, I could do this in my head. I'm just going to do that exponent, 12. That's my pOH. Now it says find the pOH if the find the pH if the pOH is 12. So I know that pH plus pOH equals 14. And if my pOH is 12, then I know my pH would be 2. 2 plus 12 is 14. So there's my answer. Next, determine the pH given that the OH is 1.2 times 10 to the minus 8. So because this is not just a 1, I cannot do this in my head. I need to use my calculator. And I'm going to find my pOH first. My pOH, I take the negative log, and I get 7.31 92. So this is my POH. And it wants the pH. So again, I'm going to use this equation where they add up to 14. All right, this last one. Determine the hydrogen concentration if the pOH is 12. So I first need to determine the pH. So the pH will be 14 minus the pOH. My pH is 1.8, but it wants the hydrogen concentration, so I need to go backwards here. So I'm going to go 10 to the negative 1.8 and then press enter. And I get as my hydrogen ion concentration as 1.58 times 10 to the negative 3. There's a couple of ways that you actually could do this. You could find the hydrogen, or excuse me, the hydroxide ion concentration first, and then you could use that Kw to help you solve for the H+. Either way, you'll get the same answer. All right, let's take pH and apply it to what we've learned before. So question number 1, what is the pH of a 0.4 molar solution of hydrochloric acid? Well, what do we know about hydrochloric acid? I know that it's a strong acid. And you can see that there's just an arrow going over to the right, meaning I'm going to have all products. And what do I know? I know that at the start, I'll have 0.4 of my acid, but when it dissociates, I won't have any of this at all. So how much of the hydrogen ion and the chloride ion am I going to have? Well, it's going to be 0.4. What is important is this hydrogen concentration, because from that I can find the pH. So again, if it's a strong acid, if they give you the concentration of the acid, that is also the concentration of your hydrogen ion. So my pH is negative log of that hydrogen ion concentration. So I do negative log of 0.4 and I get 0.397. So there's my pH. Number 2. Now this one is a weak acid. So notice that my equation is at equilibrium. So I'm going to have to use my Ka to help me solve for the hydrogen ion concentration. So write my formula, Ka equals the hydrogen ion concentration times the leftover. And then let's put in what we know. We know that the concentration of our acid is 2. And we know that every time this hydrogen ion forms, the leftover will form also. So plugging everything in, we get 6.46 times 10 to the minus 5 on this side. And we have x times x here divided by 2. I'm going to multiply each side by 2. And I get x squared equal to 1.29 times 10 to the negative 5th. And I need to square root this, both sides. And I get x is equal to my hydrogen concentration and the leftover, but we don't really need that. We just need the hydrogen concentration. And to find my pH, I have to plug it into my pH formula. And I get a pH of 1.94. So this is combining what we know about strong acids and weak acids. We would apply these same principles if I had a strong base or a weak base. So these two problems pull together everything that we've been talking about. This is called a pH square. It has all the equations that we need. So if you're wondering how to get from one point to the next, you can pause the video and use this to help you.